So, hi to everyone. Let me introduce this plenary. It is a great pleasure and the honor for me to introduce Adriano Tiribocchi, which will give us a plenary talk with the title Computational Modeling of Multiple Emulsions in Microfluidic Channels. Adriano is a colleague at the National Research Council in Rome, and before this, he worked at the University of Edinburgh in the group of NICATES. He is a world-renowned expert in active matter, droplet dynamics, and soft matter systems at large. So please give a virtual warm and loud applause to Adriano Tiribocchi. So you can start whenever you wish.
Okay, so good afternoon, everybody, and thank you, Andrea, for this very nice introduction. Let me also warmly thank the organizers and the committee for the very nice opportunity to speak, to give this talk today. And in today's seminar, I will speak a little bit about some of the research we have been doing in the last more or less 2-3 years. The idea behind is basically building computational models for this object, this multiple emulsions flowing within microfluidic channels, so in a setup which is very common in experiments. So this work has been done in collaboration with a list of authors reported below, mainly based in Rome, so Andrea Montessori, Fabio Bonaccorso, Marco Lauricella, Sauro Succi, then an experimental group in Harvard, Stefano Aime, Matteo Milani, and David Weitz, and then more recently, they join us an experimental group in Poland, Michał Bogdan and Jan Guzowski, in some of the results, if I have time, I'll show a little bit later on. So just to fix a little bit the idea, so what the multiple emulsion is, we can kind of give a broad definition of a multiple emulsion. It's a sort of a soft material, basically, in which you have smaller drops of immiscible fluids, which are dispersed within a larger drop. So this is a very broad and general definition. There are several possible configurations in which these emulsions can be realized. In the figure on top left, you see, I would say, the simplest example of a multiple emulsion, which is a double emulsion. So typically you would have the red core, which can be water, surrounded by a layer, which can be oil, and then in turn immersed in a further continuous phase, which can be water. So you would have water, oil, water emulsions. There may be also more complex configurations in which you may have alternating layers, 2, 3, 4 layers, and so on. So you have, more complex examples of double emulsions, and you also, but we are more interested in this the example in the last figure, the last picture of the figure, this multiple emulsion with distinct inner cores. So basically, you have the cores are basically the encapsulated droplets. So you have several droplets which basically do not merge because in experiments they typically include a surfactant adsorbed onto the interface of these cores, and this typically prevents, of course, the coalescence, and they are immersed in a fluid, which can be, for example, oil, and then, as before, this is surrounded by another continuous fluid, for example, water again. So we'll mainly focus on this example, and we'll see that there is an important role, for example, played by the number of the cores and the volume fraction occupied by the cores in characterizing the topological and mechanical properties of these systems when they are subject to a quasi flow. So just to give also a little bit of an overview of the, let's say, basic experimental setup used for producing this object. So there are several ways in which these emulsions can be created. I'm just showing only an example in the first cartoon. This is taken from a paper of David Weitz, in which they basically show that to produce, for example, a multi-core emulsion with a high degree of monodispersity, there is basically a two-step process. So there is a first emulsification step in which the droplets blue and red are produced from these bores, these tubes, inner fluid 1 and inner fluid 2. And then they are kind of encapsulated within the middle fluid, which can be, for example, oil. And then there is a second emulsification step. This is a very, of course, sketchy view. And then you get a final emulsion, for example, a two-core emulsions flowing within the outer channel. Of course, experimentalists have achieved a, let's say, high controllability in producing a more complex configuration of the systems. You can see on the right emulsions in which the number of cores increases, and of course you have an higher volume fraction acquired by these systems. These multiple emulsions have attracted the interest of many trade interest, yes, in many fields of let's say modern science. I just mentioning some of these. So, for example, you can have applications of this multiple emulsion in soft materials. So you can imagine, in tissue engineering. Also, they can also be used as a platform for the cultivation of as a microenvironments better for cultivation of 3D tumor cells for drug testing. They are also used for drug delivery in some cases. Typically, drug is stored in one of the cores, and then the emulsion is driven towards the diseased tissue. And apparently, the existence, the presence of this surrounding layer provides a much better control with respect to a simple emulsion in the time release of the drug. They are also used in this very nice example in experiments going on in the VITES lab. The cells encapsulated within droplets in the middle of the panel here. Basically, these are cells which are cultivated and produced, grown within these aqueous droplets, so kind of resembling, the structure of the multiple emulsions, and they are used as they are embryonic cells. So they are used to produce organoid models. So basically, organoids are sort of three-dimensional masses of cells, which are cultivated within the droplets and then are let to grow for hours. So multiple emulsion can be used also as a platform in this for this sort of studies, more of interest in biology and in medicine. And also, I most of the times like citing this last work made a few years ago by Gusowski and Gasteczki, in which they've been able to produce these highly packed configurations of these multiple emulsions, which they confine these droplets, and they have shown that these droplets display sort of topological and mechanical properties which are very similar to molecules, basically. So they've created this sort of bridge, fascinating bridge between the, let's say, the very low length scale at molecular level and the soft, and let's say the mesoscale. So basically, the idea is to use droplets as molecules and manipulating them in this way. So it's a work that has many potentials for the application, and also has a very good interest from a fundamental point of view. So, this is a little bit of an overview of the possible applications of these multiple emulsions. But the scope of our work is, I would say, much simpler than this a very complex experiment. So we basically want to understand what's the physics of these multi-core emulsions when they are driven by Poiseuille flow within a microchannel. You can see here in the figure on the left, figure A, a typical instantaneous configuration of a two-core emulsions. We have droplets 1 and 2, surrounded by this deformed layer, because there is the effect of the flow. And with these red arrows, we indicate, of course, the direction of the fluid velocity. So it's almost maximum in the middle of the channel and almost zero in the top and bottom where there are walls. We have flat walls to kind of simulate, the effect of the microchannel. Of course, this is a portion of the microchannel. The microchannel is much longer in our simulations. On the right-hand side, you have the same configuration, but with fluid velocity computed in the thermal reference of the external shell, so the black region. It's interesting to note that there are these two counter-rotating vortices, which, as we shall see, play a very relevant role in driving the internal dynamics of the core. And this is really interesting because it was unexpected and also unobserved so far, at least in simulations. So the basic questions are, of course, what's the dynamics of the core? If there are some shapes, particular shapes observed, in this either in the shell or in the cores, and also if there are new non-equilibrium city states which have been unobserved so far. So a few words about the theory, the model behind, we use to simulate, these droplets. So basically, the theory stems from a sort of generalized thermodynamic approach in which one typically describes, the mesoscale physics observed in the system using a set of hydrodynamic fields, which typically coarse grain over the molecular details of the system. So we basically don't care what happens at the molecular scale. And for this particular system, one needs the description we use is the following. So we consider a set of scalar order parameter, which is this pi, which tells you basically the density of the different fluids components. So if you have, for example, two core emulsions, 1, 2, and then there is the surrounding droplets, you need 3 different components of fluid density of scalar order parameters. Then you need the fluid velocity to describe hydrodynamic interaction, and then you also need the density of the fluid. Our fluid is in the limit of uncompressibility. Just to give a quick idea of the typical dimensions we have, the typical scales we have in our system. So basically, we are considering droplets with the diameter ranges between 10 to 100 micrometers. The surface tension is about 1 millinewton per meter, more or less. These are the this is sort of a mapping we created between our simulation experiments. The viscosity is about ranges between 0.1 and 1 Pascal per second, and the Reynolds and capillary number are generally low. So typically they fit within the usual numbers in microfluidic experiments. So low capillary number, of course, means that we expect deformation, but they are not so, let's say, strong to create the rupture of the droplets, which is an event that generally in experiments is it's avoided. So the time evolution of these quantities is governed by a set of balance equations, which are listed here. So the first of these is a set of convection diffusion equation, which on the right hand side you see the convective term VIV, and on the left hand side, sorry, and on the right hand side you see the diffusive term where there is a chemical potential MI. So this is for those who are familiar with this formalism. It is the Canelliard formulation of the dynamics of conserved order parameters. Then you have the Navier-Stokes equation, the second one, and the third one is the continuity equation in the uncompressible limit. So to solve this equation, you need an explicit expression of the chemical potential, which is given by which stems from the functional derivative of the free energy, and one has to choose, of course, the free energy. And this is so the free energy we use is you can imagine it's a sort of a generalized free energy generalization of the free energy of the Ginzburg-Landau free energy. Sorry. So it's you can recognize the first term, which is bulk term, which basically it's double well potential, giving you the 2 minima of the density of the 2 components. Then you have the interface term, basically gauging the energetic cost due to the presence of the interfaces separating the 2 fluids. And then you have the last term, the epsilon 1, which basically this is a repulsive potential mimicking the effect of the surfactant, so avoiding the overlap and the merging of the droplets, basically. So this is a sort of mesoscale representation of what we call the near contact interaction. So interaction basically occurring at the nanoscale, such as Van der Waals, electrostatic, and so on. And these are kind of included in this epsilon term here. So the simulations are run by using a hybrid free energy lattice Boltzmann. So I'm not going to discuss the lattice Boltzmann techniques here, simply because this method is very well known in literature, I think by most of you, and there is really nothing new about the method in itself. So the most important new things are about the results. So this is basically the method. So let's dig in a little bit into the results. And so as a benchmark test, we started from an isolated droplet. These are 2-dimensional simulations. So the picture A you see on the left, it's a single isolated droplet, which is at rest. So there is no fluid flow modifying the equilibrium configuration of the system. Then once you apply a Poiseuille flow, if you wait a little bit, then you would the droplet would attain a steady state, and the picture B just gives you a possible steady state configuration of the droplet, which of course depends on the typical on the Reynolds and capillary number one uses. This is a typical, finger-like or projectile-like structure or form often observed in this kind of experiments. And then on the right-hand side, once again, the structure of velocity field computed the frame of reference of the droplet. So with these 2 very well-defined counter-rotating vortices. So basically, the question is simple. So what happens if we include, if we consider more sophisticated systems, so if we include more droplets within the isolated emulsions? Typically, increase the number of the cores and also increasing basically the area fraction. So in our simulations, our area fraction, since we are in 2D, ranges between 0.1 and at most 0.5. So we are in a case in which we have low or mild diffraction and let's say a little bit less than intermediate values of diffraction. We are not diffraction, so we are not at the extreme level in which diffraction kind of overcomes, for example, the close packing fraction limit of our sphere and so on. So we are in a sort of low limit in these simulations. So let's see what happens when we consider a single core and a double core emulsion under quasi flow. So I'm switching for 1 second here from here just to show the movie. So this is the first couple of movies I'm going to show. So wait a couple of seconds, it will appear. Okay, so let's start from the beginning. So if you look at the movie on the top, it's a double emulsion, a simple double emulsion, which is driven by the Poisson flow rightwards. And basically we will see that nothing happens. So the internal core is typically driven by the flow at the leading edge of the droplets, and then it gets stuck there basically. Whereas if you look at the movie on the bottom, you would see that the droplets are initially accumulating at the leading edge, and then the droplets at the rear is captured by the vortexes, and then also the second one, and then they start to display this very nice rotating periodic motion, which lasts until, of course, the force is on. And interestingly, there are no, let's say, transitions from droplets from the upper parts towards lower parts. So this motion remains completely confined in the upper parts of the emulsion, and is completely triggered by the internal vorticity in this simulation. So as you can see, the complex coupling between the hydrodynamics of vorticity and phase field, is very important. That triggers this very nice periodic motion, which have been apparently unobserved so far, at least in simulations. And you can also see on the left the tracking of the center of mass position of the cores computed with respect to the center of mass of the external droplets, which display this very nice periodic motion. So this is what happens when you have, let's say, a low area fraction, so a very nice periodic motion triggered by the internal vorticity. Now, what happens if you include more than 2 droplets? So typically you increase the area fraction. So I'm showing another movie in which there are 3 cores and 4 cores. So a few seconds. Okay, I'm restarting it. Okay, the movie on the top shows the dynamics of a 3-core emulsion. You see that the 2 core on the bottom are soon captured by the vortex below, and they start to display again the rotating motion, whereas the droplets on the top is captured by the other vortex, and they remain basically in this configuration. Whereas if you look at the movies on the bottom, the 3 droplets on top, they start to kind of display this motion, but then since the area fraction is very high, there is a transition from the one droplet, from one of the cores, from the top of the emulsion towards the bottom. And this is completely driven by the fluid velocity. There are sort of fluxes kind of pushing the droplets from, let's say, one region of the emulsion towards the other one. And then if you wait a few seconds more, you would see that the 2 droplets on the bottom, they kind of couples, and they redisplay once again the periodic motion. So you would have 2 separate periodic rotational motions of the 2 droplets in these 2 different regions. Okay, so the important event here is this crossing we have observed. So if you look at the picture below, which is this blue plot, it basically tracks the position of the center of mass of the core, which there is this very nice transition from the top of the bottom, from the top of the emulsion towards the bottom of the emulsion. That sometimes it gets coupled with the other core. And the figure on the right shows basically the structure of the velocity field, which typically is sort of a flux pushing the droplets down. So you can see here that when you increase the area fraction, basically the structure of the velocity field, the 2 vortex structure is kind of missed, and this is basically due to the combination of hydrodynamic interaction and multi-body collisions, and the coupling of the velocity field with the phase fields that, of course, destroys temporarily destroys that structure, and triggers this transition. So if you further increase the number of the cores, then you would have multiple crossing or transitions. So basically, if you have 5 cores or 6 cores, you are further increasing the area fraction occupied by the cores, and you see that we plotted we track the center of mass position, and you see that droplets may move from top towards bottom and then going again towards top. So the more you increase basically the area fraction, of course, we must remain within, not very extremely high area fraction. So our results are valid until area fraction is 0.4, 0.5. We can see this sort of multiple crossings, which kind of trigger a sort of pre-chaotic dynamics of the course. In this slide, we basically sort of summarize what we have been describing so far. So basically, we have this simulation so that we can distinguish, the steady states between in 2 regimes, basically. So the LL states, we call long-lived states, which basically, when the emulsion is subject to a Poiseuille flow, if the area fraction is, let's say, low, we have an empirical limit of 0.3, 0.35. Then the core display this nice periodic motion, but they remain confined within either the upper or lower region of the emulsion. Whereas if you increase the area fraction, then you have transition. You can have crossings. You can have either a single crossing, for example, when n is equal to 4, or multiple crossing when you observe several transitions of droplets. So you may also imagine that this is a sort of an analogy with quantum mechanics. It's a sort of 2-state systems in which there is a sort of barrier created, for example, by the hydrodynamic interaction, which is broken temporarily when the area fraction gets very high, and there are transitions of these let's say, of course, are droplets, not molecules, from one stage towards the other one. Of course, our system is completely classical, so there's nothing quantum, but it's interesting and fascinating, kind of building this sort of potential analogy between these 2 very different worlds. And along this line, we've also used these symbols to characterize, the states, such as, for example, if you look at the picture n equal to 2. I'm just writing on the screen. I think you should see it. So, for example, if you look here, basically with symbol 1, 2, 0, we basically mean that we are in a state in which there is droplets 1, 2 confined on top, and droplets 0, and so no droplets on bottom. With the state, for example, 3, 1, 2, basically we indicate there is droplets number 3 confined on top, and droplets 1, 2 confined on the bottom. Whereas these ones are basically temporary living state, short living state, that, for example, this may decay in this further state here. This is sort of continuing the analogy with quantum physics and using the statistical occupational number, basically, that formalism. Okay, so the conclusion of the first part basically says that we have been kind of able to observe noble and equilibrium steady states, basically triggered by the internal vorticity if the area fraction is low. And this can be distinguished between 2 regimes, low area fraction and area fraction. So in one case, they show this very nice periodic motion, we also call planetary-like motion. Whereas if the area fraction is high, there is a very complex combination between hydrodynamic interaction and multi-body collisions. So you may also have a sort of pre-chaotic motions. And once again, Lattice Boltzmann has provided a good model for capturing these new dynamic behaviors, which in an everyday example of a soft material. So when I usually have given parts of this talk in the past, I mentioned some perspectives which are still working on, at least on some of them. For example, extending trying to study better the physics of these double emulsions under Poiseuille flow when one of the components is a liquid crystals, or what happens, for example, when one of the components is active, so it's self-propelled. There are some experiments going on this line. But today I would like to speak a little bit more about a project we have been developing in collaboration with the experimental group in Poland, which is about the study of this translocation of this high internal phase double emulsions, translocation through narrow constrictions, so sort of capillary-like structures, which are whose size is much smaller than these double emulsions. Much credit for this work goes to Andrea Montessori, which has written code and performed the simulations. So is the expert in charge really for this joint work. So as before, a few words about what we mean with the high internal phase double emulsion. So these are basically this is the systems in which we have a high volume fraction of dispersed droplets surrounded once again by a layer, and these are arranged in a sort of tightly packed, strongly deformed configuration. You can see here on the left typical results of one of the experiments made by Jan Gusowski and Michal Bogdan, in which you have approximately monodispersed droplets. And on the right-hand side, one of the our LB simulations. This is just a visual comparison of the two systems. So why the systems are interesting to be studied? You can imagine, of course, several possible applications. I'm just mentioning two of these. There is an interest in the microfluidic community and also in soft material scientists. Just imagine what happens when you have this HIPD crossing this narrow constriction, which is basically what we have done in our simulations now, and trying to understand what's the shape this emulsion achieves or attains when it is collected in the outer chamber. This is one of the possible structures, and there are of course several fundamental questions one may be interested in, such as if, for example, the degree of monodispersity, if it is created as a monodispersive emulsion, is preserved, or if there are, for example, topological transitions occurring within, and whether, for example, in the bulk or much closer to the periphery, what's the shape droplets attain, if it is deformed, and how it may depend on the volume fraction occupied by the cores, and by the size of the constriction as well. So there are many fundamental questions of interest, and we have tried to respond to some of this. This object also represents an interesting platform to understand more complex behaviors, for example, occurring in tumor spreading and cancer metastasis. There is this very beautiful work published a few years ago in PNAS, in which basically the authors have shown that there are these CTC clusters, these are circulating tumor cells that are capable to cross towards these very narrow capillaries, which are much narrower than the typical size of these clusters. And this was an idea that was completely unaccepted before, so it was believed that it was not possible, but they performed an experiment with the microfluidic experiments in which they showed that it was possible. And I think I have a few minutes. I can show the movie, their movie, which is a very nice movie, actually. So you see this combination of droplets that they are driven towards this very tiny channel, much narrower than their sides, and it kind of deforms in a very elongated structure in a sort of single file configuration, and it continues its motion. And the very interesting aspect of this result is that when the droplets approaches, the exit of the channel, you'll see that its structure remained highly deformed, at least within the times of the simulation, and is not capable of restoring its initial shape. So this apparently helps very much, the sort of circulating tumor cells to spread towards capillary in the human body. You see the structure is highly deformed. It's completely lost, let's say the initial shape the droplet had. Okay, so this is basically why this a couple of cases in which this HIPD are interesting. As you can imagine, this is sort of an extension of the work I presented before. So instead of having a low volume or area fraction, of course, we have a very high volume fraction or area fraction occupied by the cores. So this is typically a system we consider. So these objects are simulated using a three-component color gradient lattice Boltzmann, which you have the droplet A, the phase A, which is the droplet phase. Then you have the lubricating phase, which is the phase living between the interstices of the droplets, basically the fluid films. And then there is the continuous phase, which is in the outer part of the shell. So these are the values on the left of the typically surface tension and viscosities we use in simulations. They are basically tuned properly to approximately match with the experimental values of the given us by the experiments by Jan Gusowski, basically. So I cannot consider myself an expert in this color gradient lattice Boltzmann and much more into free energy. But basically, as you can see, the most important ingredient of this system is one of the most important, I would say, is trying to avoid the merging between droplets, right? In this system, in these simulations here that use color gradient, basically this is done by including a force field, a topological, let's say, force field that each droplet has, basically. So each droplet typically checks in its surrounding whether there is another interface of another droplets. And if within a couple of lattice sites, 2-3 lattice sites, there is another interface, then the force is switched on, and there is a repulsive force, which is basically avoids the merging of the droplet. It's a different mechanism with respect to the previous one I showed, but it basically has the same aim. So kind of providing a mesoscale representation of the near contact interaction, basically. So this is the system we are considering. So this is the, let's say, the starting configuration, basically. So on top, you see the configuration at time 0. So we start from this checkerboard structure of the emulsion, basically in order to achieve, the highest area fraction occupied by the course. And then we let the system to relax towards a sort of near equilibrium state for a few thousand time steps. And then you see that the shapes is a little bit, of course, changed, more rounded. But then, the area fraction basically is preserved, which is very important. In this particular sequence simulation, we have phi, which is the area fraction, which is 0.9, and number of droplets is 49. So this shows in order to have, a very highly compact structure of the emulsion. So the question we would like to ask is, what are the shape deformations of the emulsion when it typically translocates towards distriction, and when it's collected basically at the end? So the shape deformation becomes kind of permanent, or for some reasons they are restored to the initial shape. How this shape depends on phi and on the ratio between the vertical sides of the constriction and the typical diameter of the external shell, and what's the structure of the fluid velocity, in particular in the constriction. So this is the results we got, and I'm showing here the last movie, which is this one. So a few seconds, we start. Okay, so I'm restarting it. So basically, the movie on the top represents a simulation of this HAPD in which phi is 0.55. The second one with phi is 0.75, and last one with phi is at maximum, let's say, value achievable in our simulation, which is 0.9. So you see the droplet starts to cross, the constriction, and then they get, deformed. And typically, I'm stopping the movie just here, and typically you see that when the area fraction is low, basically the droplet has restored this sort of spherical kind of structure. Whereas if the area fraction increases, you see there are this relevant, shape deformation. Basically, the emulsion is elongated towards the direction of the fluid, but the shape is also kind of due to the fact that there has been a translocation, so towards a very narrow constriction. And you see that there is, when the area fraction is very high, there is this very tightly packed configuration, and basically the degree of monodispersity is roughly preserved in our simulation. So there are few coalescence events, which this is due to the algorithm we use. In order to understand a little bit better why this happens, we try to compute basically the local stress, the local the local stress typically present at the interfaces, and in particular touching interfaces, different interfaces living, of course, in the emulsions. So if you see that, if you look at the emulsion on top, where the area fraction is very low, you will see that the effects of this quantity, which is the modulus of the gradient velocity tensor, which gives an estimation of these local shear stresses, is very low. Whereas if you look at the picture on top, you see that there is this very beautiful interconnected network basically existing among the droplets, which kind of characterize on the structure of the system, and it persists over the entire simulations. So basically, this means that these viscous forces basically are dominating when the area fraction is very high, and are dominating over surface forces, which would like to oppose to shape deformation and kind of keep the spherical shape. So in the second configuration, viscous forces and viscous dissipation becomes, much higher dominating contribution in this sort of systems. We have also characterized these shape deformations in terms of this deformation parameter, which is the ratio basically of the area towards the square of the perimeter, assuming that the area is preserved. And you see that keeping if you look at the picture on the left, if you see that keeping the height of the constriction constant, this parameter correctly tracks the deformation. So if you look, for example, in the red plot, you see that it is initially around 0.8, rate, which is when you have the highest area fraction. Then it gets low, very low, when the emulsion crosses the constriction, and then it basically remains constant at a much lower value than the initial ones, basically meaning that the deformations become permanent in this configuration. Whereas if the area fraction is low, you see that if you look at the first plot, the white circles, they are basically restored to 1. So there is a strong dependence of the let's say of the dynamics of the systems from the area fraction, but it's also an important dependence on the height of the constriction. So we also computed the residual deformation, which is a time average value of lambda once the translocation is completed. And you see, for example, if you compare the plot pluses and the asterisks, you see that diminishing, the size of the constriction, keeping the diameter the same, there are much stronger deformations in the system. So there is also an effect of due to the constriction, which for narrower constrictions, the structure of the emulsion is much more deformed and elongated. Finally, we also computed the fluid velocity within the constriction, and in particular, you can see very basically that out of the emulsions, the fluid velocity is basically unidirectional, so it's constant in unidirectional. Whereas within the emulsions, once the emulsion has crossed the constriction, you see that there are important fluctuations, basically due to the complex coupling between fluid velocity and interfaces of the different cores. Also, the ordering of the droplets is important, modified by the let's say the passage towards the constriction. So we computed the plot below, the number of hexagonal clusters observed counted within the emulsion. So basically sort of having an idea of this sort of crystalline-like order. So it's rather high before, let's say higher, before the emulsion crosses the constriction, then it gets very low when the emulsion crosses, so there is a very much decrease of crystalline order, and then there is, sort of restoring of the crystalline order if the area fraction is low. Whereas if the area fraction is very high, then you see the red plot that, let's say the sort of crystalline-like order is basically lost. From this last presentation, we can conclude basically that, first of all, we have been able to simulate, much credit once again goes to Andrea Montessori for the very beautiful work. We have been able to simulate, the translocation of the emulsion. And we have seen that, the shape, the final shape you get in the outer chamber mainly depend on the area fraction of the course and on the height of the constriction with respect to the diameter of the droplets. And of course, there is much work to do, in particular, a much deeper characterization of the topological and logical aspect of this mixture, such as, for example, looking at if there are the topological transition, identification and tracking of the motion in internal drops to understand whether there is a sort of an equation of motion governing their dynamics. And also, for example, if there is a possibly yield stress, kind of saying when there is a possible transition from a solid-like behavior to a possible liquid-like, if these are the two regimes we have observed, if they are correctly captured. As a final statement, once again, I would conclude saying that lattice Boltzmann has provided a fully, at least in these two cases, but we've also used in other situations, a fully fledged platform to able to capture the mesoscale physics of this complex state of flowing matter. I've shown some of them, such as multiple emulsions, soft granular fluids, and so on, and basically relying on a mesoscale description of the physics, just completely neglecting, what happens basically at the much lower length scale, such as the nanometer or the molecular scales. So I'm finishing, just thanking everyone for the attention, colleagues, and also the ERC for funding the project, and the CNR for hosting our research and our work. Thank you very much for your attention. I'm open to questions, of course.
Thank you so much, Adriano. Yes, we have time for questions. If you have questions, please raise your hand or write it on the chat. Okay. Wait. Okay. if there are no questions, I would like to thank again Adriano for this beautiful
Thank you very
speech.
much.
And I think we can proceed with the conference now and with the technical session. Thank you very much, Adriano. Adriano, continui tu con.
Yes, now I am the chair now. So this switch. Okay, give me a few seconds. Okay, so okay, I'm just removing that.
Now I think you are the organizer.
Yes.
So, perfect. Okay.
So the next speaker. So let's start with this with the session, the technical session boundary conditions. Next speaker is Schwarzenmeyer. Yes, I'm giving you the rights to share the screen. I think you should have them now.
Yeah.
Okay. So let me quickly introduce Christoph Schwarzmeier. He will speak about analysis and comparison of free surface lattice Boltzmann boundary conditions. So there is a question from Boccanegra, I think, you raised the hand.
So may I start?
Okay. Yes, you can.
All right. So thank you for the introduction. My name is Christoph Schwarzmeier. I'm from the Chair for System Simulation at the University of Erlangen-Nuremberg, and I'm a PhD student under the supervision of Professor Ulrich Röde. So in my presentation, I will talk about the free surface lattice Boltzmann method, which I will introduce at the beginning. I will then talk about its boundary condition at the free surface. We will then perform a boundary force balance computation, so a somewhat theoretical analysis of the boundary condition. Then I will show you two numerical experiments. And finally, of course, I will provide a summary and outlook in my references. But let's start with the free surface lattice Boltzmann method. So the free surface lattice Boltzmann method simulates a single phase fluid flow where we have a free boundary. So that means we only simulate the fluid in the heavier phase. We ignore the lighter phase. So we implicitly assume that the dynamics of the lighter phase do not contribute significantly to the system and can be neglected. And this is suitable for simulating two-phase systems where we have very large or even infinitely large density and viscosity ratios between the two phases. So here I'm basing my work on the free surface lattice Boltzmann method that was introduced by Caroline Körner in 2005. And as you can see, we have already applied various applications to this free surface lattice Boltzmann method. So the very basic concept is simple. So we partition our fluid domain into several cell types. So the first type of cells are the liquid cells, where we have a fill level of 1, and these cells do contain particle distribution functions. On the opposite side, we have the gas cells. The gas cells are empty, so they have a fill level of 0, and these cells do not contain PDFs. And in between, we have exactly one layer of interface cells, and these interface cells are characterized by having a fill level that is between 0 and 1, and these cells also contain PDFs. So the fluid flow is now only simulated in the liquid and in the interface cells. The gas only interacts with the liquid by pressure, and we do not model any shear stresses in the gas. Algorithmically, you can say that a very, very simple version of the free surface lattice Boltzmann method could look the following. First of all, we compute the interface normal, so the surface interface normal, because we need it in the second step, which is, first of all, the LBM streaming step. But second of all, we also need to reconstruct those PDFs that are coming from the gas side and streaming into the interface cells, because as I said, we do not have gas side PDFs. And then we need to exchange the mass in the interface cells, which means that the interface cells can fill, they can empty. And then we perform an LBM collision. Then we perform cell conversions according to the mass exchange. So for instance, if an interface cell has filled to a fill level of 1.1, we will then convert the cell to a liquid cell. But then we also need to distribute the excess mass of 0.1 in my example to the other cells that are surrounding it. So let's have a look at the boundary condition. So as I said, streaming is somewhat more difficult here because first of all, we have gas cells, and those gas cells do not have PDFs. However, on the opposite side, we have liquid cells and interface cells. And whenever those cells are involved within each other, or those two cells to each other, then we have a regular LBM streaming operation. But on the other hand, if we have interface cells, then no PDFs can stream to the gas cells, because in the gas cells, we don't need PDFs. But from the gas cells to the interface cells, as shown in the image here, we actually need PDFs. And those PDFs are not available. So shown here in light gray, so they must be reconstructed. And very simply spoken, what should the boundary condition fulfill? Well, at the interface, the boundary must balance the forces that are coming from the liquid and the gas, so the gas pressure. That's why we simply use a anti-bounce back pressure boundary condition that is shown here. And we have as an input then the gas density, so the gas pressure as it is directly proportional in LBM, and then the interface velocity, so the macroscopic interface velocity. And just for the sake of completeness, I'm following the notation that is used in the original paper. So FI out means PDF, that is the PDF after LBM collision, and those EIs are the discrete lattice velocity vectors. And whenever you see a dash, this is actually then the inverse particle distribution function. So as I said, we do not have those PDFs available, so we need to reconstruct them. The straightforward way would be to say, okay, all those PDFs that are missing, let's simply reconstruct them, and that's it. However, in the original paper, the authors argue differently. They say we need not only to reconstruct those PDFs that are actually missing, so in the image on the left, those 3 PDFs, but actually we need to reconstruct all PDFs that are coming from the opposite direction of the interface normal. So the 4th one here is also reconstructed, although it is already available, which means we are overwriting existing information. And the authors justified it by saying, okay, only then the forces at the interface is balanced. But let's have a look at this here. So first of all, the basic assumption is that we say force F by a fluid on a surface element A is exactly equal to the momentum that is transported by the particles streaming through this element during one time step. So essentially, we have this kind of balance equation where we say, okay, we have some PDFs on one side of the interface, and we have the PDFs on the other side of the interface. The PDFs on the right here, all those are reconstructed, and on the left, they are not reconstructed. And as you can see, we already shifted the velocity frame by the reference velocity, so the macroscopic velocity, just to be sure that we are Galilean invariant. So if we now plug in the pressure boundary condition that I've shown earlier in this equation, the authors say, well, this eventually results in an equation at the bottom. So we have the force on the left-hand side and the gas pressure on the right-hand side. However, I actually do have 2 issues with their analysis. First of all, they completely ignore the center PDF. So the index I equals 0, while it must mathematically actually be treated to be part of the set that is shown here. And second of all, I have seen that the equation have actually been reshaped incorrectly. So to be more specific, the very first line of this equation is supposed to be 0 if the analysis of the authors is correct. However, if you really perform that and if you really compute everything, you see that this is not 0. So we have some other terms that are disturbing here. And my suspicion is that the authors initially formulated this force balance in a way that does not respect Galilean invariance, and then just added all those velocity shifts here. But as soon as you do this, the force computation is not balanced anymore. But now let's do a corrected version of this force balance computation. So let's assume that the center PDF also needs to be reconstructed, because as it is formally part of this set, as is formally part of the opposite direction of the interface. So if we do that, we see, okay, on the right-hand side, again, we have the pressure and also a kind of large disturbance term, an error term. Second, we can also say, well, let's not reconstruct the center PDF because it's already available. And again, if we do this analysis, you see we have the pressure on the right-hand side, but again, we have kind of a large error term. So these error terms, as you can see, are dependent on various things. So it's really hard to make a general estimate of which error is larger or smaller. But anyway, so the authors initially argued that we reconstruct more PDFs than are actually missing, only due to the fact that force is only balanced if we do it that way. However, as we have seen now, force is not balanced in any of these approaches. So let's say, why not only reconstruct those PDFs that are actually missing? For this purpose, I have defined various sets. They are not too much of importance here. I'm just skipping over that quickly. But if we perform this analysis, then you see again, okay, we have the pressure on the right-hand side, which somewhat balances the force, but nevertheless, we have also a large error term that is dependent on various different things. So to quickly summarize, we can see that the error in the force balance depends on so many things that it's not possible to make a general error estimation here. So we need numerical investigations. And my first numerical setup is a capillary wave. So it's standing wave with a wavelength of 100 micrometer. And the good thing about this setup is that we have an analytical model available. So the simulation setup is quite simple. I have a resolution of 100 by 100 cells. The domain is periodic in all directions, and we've simply used the fluid properties of water. And as you can see, so I've initialized simply a sine curve here when the video starts over, which is then influenced by gravity. So you can see again. And what I'm doing now is I'm tracking surface elevation at exactly this point. So at the second initial peak, which means it's 75% of the domain in horizontal direction. And that's where I'm monitoring the surface elevation. And that's what you see here in my plot. So in the continuous line is the analytical model that monitors this point, and all the other curves are from the experiments. As you can see, initially, all those curves are almost identical. There's not too much of a difference, but as soon as it gets somewhat later in the simulation, there are some differences. I should mention that these staircases that you can see here, they are really due to the resolution. So essentially, if you have here a staircase at the end, this is really one lattice cell that you see here. But anyway, so first of all, we can notice that the normal-based approach where we keep the center PDF, so which is orange here, and the other one where we reconstruct only missing PDFs are almost identical. So it's hard to, well, I don't know whether we can reasonably say that they differ here. But anyway, you can see that the normal-based approach where we reconstruct the center PDF actually shows kind of oscillations at the end, which are, well, probably not physical at all. But let's have a look at that in the video. So while you will see that the other two kind of start to move eventually, the third one, where we reconstruct the center PDF, somewhat begins to oscillate. Essentially, my simulation at a certain point stopped, but I believe it could even happen that this simulation gets unstable later on. But let's look at a different test case. So I have also simulated a two-dimensional dam break scenario. So it's a collapse of such a liquid column. I have experiments from a paper from 1952. Martin and Moyes are the authors. And the simulation setup is also simple. So we have 240 by 480 cells initially for this liquid column. The two-dimensional domain is a periodic in the third direction. So in the screen direction, it is periodic. On the horizontal walls, you have no-slip on-spec boundaries. And at the vertical walls, you have fluid-slip boundaries. And again, we are using the fluid properties of water. And gravity acts here in the direction to the bottom. So the liquid column eventually collapses. And I've also used the same dimensionless values as the authors in the original work of the experiments. And I'm plotting now the column width over time, so the spreading width and the height of the column. So I'm plotting it here. And as you can see, the experiments, again, here in red shown, they are fairly close to my simulation. So the simulation is arguably good. You can see a difference between the approach where we reconstruct only the missing PDFs, but the normal-based approaches seem fairly identical. It's hard to really say which one is here more accurate, and it's even harder if we look at the height of the liquid column. So you see those are basically identical. so all my simulations. However, that is actually not the entire truth. So because I'm looking at the shape of this liquid column now. So after a certain time, we have such a shape. And this is the normal-based approach where we reconstruct the center PDF. Now look closely, I'm switching to the next slide, where we have the normal-based approach that keeps the center PDF. And as you saw, or maybe you didn't see it because there is almost no difference. So really just a minor difference. However, I'm switching now to the third approach where we really reconstruct only those PDFs that are actually missing. And you will see, first of all, the shape somewhat differs to the other two. But even more important, at the bottom here, you see some gas inclusions. I'm going to zoom in on my next slide. You see that the bottom is not really fluid anymore. So it's some inclusion of gases. So in a certain way, it doesn't wet the bottom anymore. And this is definitely a problem and should be investigated more in the future. So to summarize all my numerical investigations, I'm directly jumping to the final summary of my talk. So first of all, we have seen that neither of these approaches balances the forces at the free boundary. A general error estimation was not possible because we have this dependency on various things, such as the specific PDFs in a simulation, such as the macroscopic velocity at a certain point and so on. So the numerical investigations, on the other hand, revealed that, first of all, the normal-based approach where we reconstruct the center showed some unphysical behavior and oscillations in our capillary wave test case. The approach where we reconstruct only missing PDFs showed some artifacts near solid bounce-back boundaries. They should be investigated. And finally, we have the approach where we follow the, where we base it on the normal, but keep the center PDF. And this seems to be preferable so far. However, we definitely should investigate it more. So we do plan to perform some three-dimensional numerical investigations, especially to, for instance, evaluate things like the rotational symmetry and yeah, for instance, rotational symmetry. When you have a rotational dam break, then dam should break in a rotation in a exactly as a circle, and we will investigate whether it does it. And we have also the idea that we test other approaches. So we can also say we do not only reconstruct those PDFs that are missing, but we say we can reconstruct at least a certain amount of PDF. So it can happen that the system is probably underdetermined, but we also have to investigate that. So with this, I want to thank you for your attention and want to conclude my talk.
Okay, thank you very much, Dr. Schwarzmayer, for the nice talk. We're open to questions. I think you already have some. If you look at the chat, there are 3 or 4 questions, so I think we have time to reply a few of them.
So the first question is whether the Laplace pressure is taken into account in the first test. Yes, the Laplace pressure is taken into account. So the second question is mass conserved with the new boundary condition? So the new boundary condition does not affect mass conservation. Mass conservation is only then issued when you really exchange the mass. And this is a different step of the algorithm in the free surface lattice Boltzmann method. So another question is, does mass redistribution method in the last step affect the accuracy of the numerical tests? So I didn't really show about the mass distribution here. And we have actually only one way of distributing the mass, which is the way that was also formed by Caroline Körner in the original work. So I do not really know how to answer your question. So I bet it does, but it's basically just this approach that is available here. Then another question is, what would happen to a single gas pixel inside the fluid? So a single gas pixel inside the fluid is surrounded by interface cells, because that's a strict requirement of the algorithm, that it is always surrounded by interface cells. But essentially, it is kept because mass is conserved. So it still gets treated by the code. The problem is, just to mention that also, that we, in further steps, for instance, for the Laplace pressure, we need the curvature of the interface. And of course, if you just have a single gas pixel, then the curvature computation is not really meaningful. So essentially, most likely we'll get unstable here. So another question is, how do we evaluate the cases when the most PDFs are unknown? So those PDFs, so you could, for instance, say, so you essentially in the algorithm, you can just check how much PDFs are unknown. So I can say, okay, how many gas neighbors do I have and in which direction? And so I know how many PDFs are unknown here. So, and finally, what do you think about numerical approximation of the surface tension influence on possible oscillations? So it is of course possible that higher surface tension could somehow dampen these oscillations. So in my test case, I have used exactly the surface tension that is required by the test case. So I do not really think that this is the cause for these oscillations that you have seen in the capillary wave scenario.
Okay, there would be another question, but I think we can stop here for the moment since we are a little bit over time. And then, yeah, thank you again. Thank you very much again for your very nice talk and reply. So we can go to the next speaker, Francesco Marson, I think.
Yes, it's correct.
Yeah, okay. So we will speak about unified formulation analysis and improvement of all link-wise Dirichlet velocity boundary schemes. I think you have the right to share the screen. Just
let me try. Can you see the presentation?
Yes, we can. Yeah.
Okay.
So, please.
Perfect. So, okay, thank you for the presentation. I'm Francesco Marson, and I'm a PhD student at the University of Geneva. And today I would like to speak a little bit about our research regarding directional lattice-Boltzmann boundary condition, and in the specific about the unified formulation and the extension to parabolic schemes. So to begin with, I would like to consider this showcase on the right-hand side, where we have a very densely packed simulation of, for instance, a porous media application or a suspension flow, for instance. And what happens in this kind of simulation is that increasing the resolution is very expensive, so it's much more convenient to increase the accuracy of the boundary condition. But what happened if we run this simulation at the very coarse level, then we will have many narrow channels with very few mesh nodes. And also we will have many boundary nodes, and actually the number of boundary nodes can be even higher than the number of bulk nodes. And with boundary nodes, I mean nodes where we need to apply the boundary condition. So what it is important in this situation is to have boundary conditions that are really accurate, but accurate at the coarse level and also able to perform locally, so also with a single node available. Then we will also need the stability and optionally also parameterization. What does it mean, parameterization? Well, a boundary condition that is parameterized has the characteristic that its error does not depend, depends only on the numerical, on the non-dimensional numbers that characterize the flows. This means that, for instance, its error does not depends on viscosity or in the symmetric relaxation rate. And the typical situation you will see is the one in the right-hand side in this graph, where a non-parametric boundary condition, you will see that its error will increase generally, at least increasing the viscosity. So, how do we develop good, so accurate boundary condition for this kind of application? Well, the strategy is to start us to studying very elementary flows like straight channels, horizontal channels, or inclined channels, and then increasing progressively the complexity of the simulations and of the flows, such that we are able to analyze the errors that pop up, increasing the complexity of the flows. It has been shown that accurate boundary condition also in this very simple test case, then we'll be having accurate way also in complex flows like porous media. So now consider, for instance, this inclined channel on the right-hand side that is discretized in a very coarse way with very few nodes. Now we want to resolve this channel considering a link-wise boundary condition. That means that we want to resolve through independent operation the boundary along each lattice direction. As you can see, we have very few nodes, and some of them are double boundary nodes, means they are boundary nodes for the two sides. What it is known in this kind of situation is that it is possible to correctly, so exactly, resolve a co-ed Stokes flow at steady state, also with a single node boundary condition. For instance, the recently proposed ELI boundary condition. But what is also known is that till today, it is impossible to have an exact solution for a Poiseuille flow at steady state in a Stokes flow. And this is impossible also in the case of a horizontal channel, so aligned with the nodes. So what we propose, we developed a new correction that is able to deliver exact solution for this problem, also with a single node boundary condition that are local in time and space. This was previously a unique features of advanced multi-reflection schemes that are non-local. At least we are talking about directional boundary condition. Now, before going further, just a summary of my notation. So we'll denote with the letter E the equilibrium, with the letter N the non-equilibrium. Then the hat will mean post-collision. The index I bar will be the index of the direction pointing towards the wall, and I the opposite direction. Then the relaxation time will be tau plus and minus for the symmetric and the antisymmetric, and equivalently lambda plus and lambda minus. It is just tau shifted. And then we will have the magic parameter that will be the multiplication of these two relaxation times. Well, I emphasize here that okay, I'm talking in the context of the TRT collision model, but the results are not limited to TRT. They can be extended to MRT, and the considerations are the same for BGK. But in this case, it is convenient to explain in this framework. Then I will use the Champagne expansion for the post-collision non-equilibrium, as it is shown here. And finally, I will use the symmetric and antisymmetric decomposition of the population. Again, this symmetric antisymmetric decomposition, you can do it with any type of collision model. Well, we realized that we can represent any type of link-wise directional boundary condition in lattice-Boltzmann with a unique formulation. So we have different family with infinite number of type of schemes, and they can all be represented by a linear combination of equilibrium and non-equilibrium that you see here on the right. In the specific, you have a linear combination in the first line. Then you have these pink terms here that are some terms that we use to represent with this unified formulation a recently introduced ELI scheme that is a fully local scheme. Then we have this K- correction that we will use to parameterize and improve the accuracy of the schemes. And then we have this term here that basically is the influence of the motion of the wall. So introduce the wall velocity in the scheme. So now from this type of representation, we can introduce also an additional representation that is somehow more useful and to develop the boundary conditions. And the idea basically is to transform this term here into this term here. And we do that with the following steps. First, we decompose the population in equilibrium and non-equilibrium part. then in symmetric and anti-symmetric component. Then we use the Champagnat expansion I showed you before on the non-equilibrium. And finally, we perform a Taylor expansion such that we have all our quantities at the same time step and at the same boundary node location. Doing so, we are able to have a new set of coefficients that this time are going to multiply the equilibrium at the boundary node and its directional derivatives. Here we have the closure representation at steady state. Now, from this representation, we can single out the terms that are important to have an accurate linear velocity representation. Other term that is important for the linear pressure representation. Then we have the terms important for parabolic profiles for pressure and velocity. And finally, we have our closure corrections. Here, it is important to notice that these new coefficients of the closure relation of the equilibrium are linear combination of the geometrical coefficient that defines the boundary schemes. Finally, this alpha plus and alpha minus in the closure relation plays the role of free prefactor. In fact, they are the prefactor. If you do that, the Taylor expansion close to the boundary, you will realize that are prefactor of this expansion. So somehow they are free parameter that allows us to say that we have some family of schemes that are made basically of an infinite number of schemes. Now, let's go to consider these K- corrections and what we have new from this point of view. So usually this K- correction has been developed to give parametrization to the boundary conditions. Now we can apply this K- to different families of schemes, like the classic linear schemes, the LI. One of the most famous boundary condition in this family is the Buzidis scheme, for instance. And if we apply this correction, then we get parametrization. But what we have realized is that we can develop new correction that are able to provide parabolic velocity in the Stokes flow, so exact parabolic velocity profiles, or linear pressure in Stokes flow. And these type of corrections also give a parametrization in the case of single node schemes. Moreover, they can be applied to all the schemes inside these families. This correction will give the same accuracy at steady state for all the families of schemes we are at which we are applying this to which we are applying these corrections. Now, let's consider the classification of the different linkwise scheme on the base of the Stokes flow. As you can see, the most known boundary conditions are all located in this region of the graph. So, like the Buzidis scheme, the U scheme, but also the Filipov-Haenel and the Meil-Cauchy. So they are boundary conditions that are able to provide linear velocity and uniform pressure accuracy. Then we can correct them in order to have, with the K1 correction, to have a parameterized behavior. And in this case, we go from this Li, ELI, and FH to the equivalent parameterized version. Actually, not for the Filipov that we cannot parameterize. Then we have the equivalent accuracy, but with a parameterized behavior. Here we have the ELI schemes that are somehow a subfamily of the general LI scheme. But now with the new correction, we have new boundary conditions. So the new AELI and LI schemes that are able to give a correct linear pressure profiles, and the ELI and LI free that are able to give parabolic velocity profile in an exact way. Also, we have also applied the K-free correction to Filipov-Haenel, giving it the parabolic velocity accuracy, but not the parameterization characteristic. Also, I represented here the multi-reflection schemes and some new advanced multi-reflection schemes that are somehow more advanced because they are capable of at the same way having a parabolic accuracy for velocity and linear pressure accuracy. But we will see that also the scheme with K3 will be very accurate on real test cases. And yeah, I forgot to mention that these multi-reflections are non-local anyway. Here another classification that I will skip, but you have it if you are interested. Now, I want to mention that, okay, from till here we have spoken about the Stokes flow, but our analysis is not limited to Stokes flow. We are also analyzing the behavior at finite Reynolds number. We have extension for advanced multi-reflection and for Couette and Poiseuille flows at Navier-Stokes level, and analysis of time-dependent accuracy. Indeed, all the families that I showed, also all the specific method we have inside each family, does have the same accuracy with the correction at steady state, but they have different stability properties and time-dependent accuracy. Regarding stability in particular, we also realized that we can use the same stability condition we have in the bulk, that is the one here in the blue box. We can reformulate it in an equivalent way for the boundary if we interpret our boundary condition as a modified collision step. Then the condition will be very similar, but we will have also some coefficient of the closure that will pop up in this condition. And given that we have the alpha minus free parameter, this alpha minus free parameter will be inside, in this case, this beta will control also this beta. So we will be able to control actually the stability properties of the schemes with tuning this parameter. So we are able to single out the most stable boundary scheme in each family. Here I show a result. So comparing our condition of stability that is plotted with lines, and the actual unstable simulation with the different schemes in a P-flow. And as you can see, we can predict correctly the stability regions of the schemes. And also important to notice here that the most challenging region for stability is the region at low relaxation rates. And also, as the other very important thing to notice is that if we decrease the value of this alpha minus, we are able to find boundary conditions that are more stable. So we are also developing some condition to optimize the stability of the schemes. Now, some results regarding the accuracy. Here we have a Stokes Silcora-Couette flow, where we compute the L2 error, so the loss 2 error. And we compare the result of our different corrections and also multi-reflections with a FEM solver. In this case is the COMSOL solver with body-fitted meshes. As you can see, with the K3 correction, we are very accurate for any values of the magic parameter, even more accurate of a more advanced multi-reflection scheme in this case. Then we also computed the error on the computation of permeability with the Darcy law. Here we have a simulation through an array of cylinders. Again, we compare against the FEM solution, either comparing it with a simulation with the same number of nodes as the number of cells in the FEM simulation, that is this case here, or a FEM simulation with the same number of cells than the number of nodes we have in a gap. That is this mesh here. In both cases, in this situation, we are able to be more accurate than the FEM solver, specifically with the K3 and the multi-reflection boundary conditions. Then here we have, we repeat the result at a higher resolution with similar results. And finally, some result with very narrow gaps. in which we compare again against the finite element solver with a two cell between two cylinders. And instead with our lattice Boltzmann, we are working either one with gaps of 1.8 or 0.7. And again, also here we can be competitive with the FEM solver. And also here we are somehow using an hybrid simulation where we are using the multi-reflection where is possible. But when the gaps are too narrow, we switch to ELI boundary scheme. Finally, just very few words on our work at finite Reynolds number. So we are analyzing the accuracy for increasing Reynolds number, and we realized that to preserve a higher accuracy, to increase the Reynolds number, we have to properly scale the magic parameter with Reynolds. Specifically, the best accuracy we get it when we reduce the value of the magic parameter quadratically with the Reynolds. This will be challenging for stability, of course, but we are planning to study also in relation with the stability optimization. So to conclude, we have unified and analyzed all directional scheme. We have reformulated the recently proposed ELI scheme, that is a local single node scheme, as a LI scheme plus a K plus correction. We have applied the K1 correction for parameterization to all the schemes, and then we developed two new corrections able to provide parabolic accuracy at steady state Stokes flow and linear pressure at steady state Stokes flow. Then we also analyzed the advanced multi-reflection scheme like the AVU-MR that is exact in C-flow Navier-Stokes, and also the new developed MR-NSE for P-flow Navier-Stokes that will be exact. Then we showed that we are pretty accurate compared with the FEM solution in some interesting test cases. And a few words on on other works we are working is that we are also analyzing the mass leakage in relation in specific with the solvability condition. So with this, I end my talk, and I'm open to your question. Thank you.
Thank you very much, Dr. Marson, for the presentation. So I already see a question for you. In the chat.
Yes. So I go from the last one. So no, these schemes do not conserve mass, but this is so the problem is that we are not supposed to conserve mass because the solvability condition poses a limit on the leakage, on the mass leakage. So we are anyway we're currently working on this analysis, but this will be more or less the conclusion. This is the other one is for me or not?
Yes, so far. Let's wait a few seconds if there are other questions. Yeah, perhaps there is another one. Okay, no. Okay, so if there are no further questions, I think we can thank again Dr. Marson for a nice presentation. We have coffee break now. Then we see at 16:20 for the last talk of today. So thank you very much again.
Thank you. Goodbye.
Okay, so welcome everyone to this last talk for today. I think we can start. So the next presentation is from Friedman class. We speak about non-reflecting boundary conditions for multi-speed lattice Boltzmann methods. So please, Dr. Klaas, you have the right to talk.
Okay, thanks for the promotion to doctor, by the way. I'm a PhD student from Wuppertal, and welcome from my side. I hope you can hear me and see my slides just fine. Quick note, shout when not. Yes, as introduced, I will give a talk about non-reflecting boundary conditions for multi-speed lattice Boltzmann methods. And I will start with a quick motivation of this topic and then turn my attention to some non-reflecting boundary conditions, namely the perfectly matched layer approach, the locally one-dimensional inviscid boundary condition, and the discrete artificial boundary condition, then turn to numerical results, and then give a quick summary when closing this talk. So turning to the motivation, why even bother with non-reflecting boundary conditions? So non-reflecting boundary conditions are an important concept when it comes to imposing artificial boundary conditions, namely putting boundary conditions where normally there is no boundary. This will arise in settings where the physical domain, is typically very, very large or perhaps even unbounded. And to illustrate this concept, let's say we have this flow situation here where a vortex is convected to the right-hand side, and we are not interested in the shaded area here. So we actually want to truncate the computational domain here. And if we do this in a naive way, say we put a simple extrapolation boundary condition at precisely this point, then we get away with a smaller computational domain. However, this boundary condition will impose some unphysical behavior. Since there is no physical interaction happening there, the fluid is supposed to just exit. However, you see clearly in the lower panel here that considering the modulus of velocity of this flow, there is some distinct reflection going on. And now the question is, can we improve this behavior, and which kind of boundary conditions can be employed to do this? And this motivates the need for non-reflecting boundary conditions, which precisely do not have this feature. And
Friedman, sorry, 1 second. So I think there is a problem with the voice, which is not very loud. So if you can kind of level up the microphone, the level of the microphone.
Okay, let me see. I think I even have the settings open. I can put it to, oh, is this better?
No, it's much better, yeah.
Okay. So sorry, but I hope it was clear so far. Yes, to maybe rephrase here, we need non-reflecting boundary conditions to pose here to get rid of these reflections happening here. And for the second part of the words in this title, it is about multi-speed velocity stencils, and typically multi-speed velocity stencils come from a higher order, typically Gauss-Hermite quadrature of the velocity space. And this has conceptually nice features because it has been shown in this paper by Siebert and co-workers in 2008 that this can lead to improved stability and support a broader range of supported parameters. And it is also a very promising candidate for simulation of high Knudsen and or even thermal flows. However, it comes at a cost. Not only it is computationally more demanding, also boundary treatment is more complex because having now a displacement of 3, as you can see in this depiction of the DQQ17 velocity stencil here, we now have 3 layers of boundary nodes to treat, and poor boundary conditions may well be able to cannibalize this conceptual gain from the higher order lattice and the higher order quadrature. And the merging of these two concepts, at least to my knowledge, has not been done in literature. So we were curious to see what happens when you use non-reflecting boundary conditions in the multi-speed setting. And we wanted to have a look at this. So we turned to non-reflecting boundary conditions. And the first thing we looked at was the perfectly matched layer approach, which has been extended to the lattice Boltzmann framework by Najafi Yazdi and his co-workers in 2012. So the idea here is actually quite simple. We have a computational domain, and we attach an additional damping zone of a certain width, W, in lattice nodes to that. So if we consider here a non-reflecting right boundary, we will attach this damping zone to the right-hand side. And in this damping zone, well, the name is a bit speaking, obviously, we want to damp and absorb reflections. So we design, eventually, we modify the collision operator in this PML zone to obtain precisely this, as it was shown in this paper here. And technically, now this is not a boundary condition, but since we are using damping, we can well get away with using a standard boundary condition here on the right-hand boundary. And just a remark, this perfectly matched layer is called perfectly matched because this fluid damping zone interface is perfect in the sense that this interface is designed to not cause any reflection. And to maybe give quickly just very few details about how this is working. I already mentioned we will modify this collision operator. And this is based, what one does is one decomposes the distribution F into equilibrium and non-equilibrium parts, and then also proceeds to distribute, to split again the equilibrium distribution into a mean equilibrium and some acoustic perturbation from this mean equilibrium. And eventually one gets this expression here for the collision operator omega PML, which depends on this damping coefficient sigma, and this damping coefficient sigma is controlling the strength of the damping. It is a tunable parameter of this approach. And eventually what one operatively does in the whole LBM algorithm is in this damping zone, we modify the collision step and simply add this PML, omega PML operator on the BGK operator, for instance, if we're using BGK, and then use simply this omega in this damping zone. So to sum up, the idea of this approach is that we introduce an additional damping zone with a certain width W and a certain damping strength parameter sigma, and then damp out reflections. And another, I think, very popular approach is the Lodi approach, so the locally one-dimensional inviscid approach. And as the name perhaps suggests, the idea here is that on the boundary we solve one-dimensional Euler, namely inviscid equations. So we neglect the parallel derivatives on the boundary, and we also neglect the viscosity. Why are we doing this? Because this will give us a hyperbolic system in the unknowns density and velocity. So the macroscopic values we are interested in having information about when doing simulations after all. And since this is a hyperbolic system due to dropping the viscosity, we are able to diagonalize this matrix A and eventually obtain an expression for the amplitude variations of the characteristic waves, which are encoded in this vector L here, that is essentially composed by this spatial derivatives of the macroscopic fields and the eigenvalues of this matrix A. So this we call characteristic analysis, and now we can neatly distinguish between incoming and outgoing characteristic waves by the sign of the eigenvalues of this matrix A. So just to give an example, for a right-hand side boundary of the computational domain and for subsonic flow, this eigenvalue lambda1 will be negative. So this characteristic, associated characteristic wave, the first component of this vector L, will be an incoming characteristic wave. And to achieve a distinctly non-reflecting feature, at least for the direction of the x-axis in this case, we can simply set the incoming wave amplitudes to 0, namely we replace this vector L with some adapted vector L bar, and then solve this macroscopic PDE. I have shown you just one slide before, and this will give us the macroscopic target values we should impose on the lattice, eventually on the boundary. And of course, there is a certain degree of freedom, and any Lattice-Boltzmann-Dirichlet boundary condition will do the trick, and be stuck here with non-equilibrium extrapolation. I think one could also just impose the equilibrium in principle, but this will lead to some wrong gradients. And a quick remark, this is technically only feasible for macroscopic hyperbolic systems and doesn't really fit the compressible Navier-Stokes equations exactly. But nevertheless, it is a popular approach in the lattice Boltzmann community, and we were curious to see what happens when we extend this to multi-speed. And one problem immediately arises. So coming back to the DQQ17 stencil and still sticking with the right-hand side boundary, we have the following situation depicted here. We have some last bulk nodes, and then we have 3 layers of boundary nodes. So we need to do this characteristic analysis basically in 3 columns of the computational domain. And doing this layer-wise just experimentally turned out to be numerically unstable and didn't give any meaningful results. So we resorted for simplicity to this following thing. We did this layer-wise characteristic analysis as outlined a few slides before, and then resorted to simply averaging the resulting target values over this, over the boundary layers. This certainly can be improved upon, and this is actually an open problem where we need to investigate some thought. But before seeing the impact of this in a benchmark problem, we will turn to the discrete artificial boundary condition. In this boundary condition, the idea is to approximate a larger domain with a finite memory approach. This just means that at a given time step tk, we solve a so-called lattice Boltzmann subproblem, and we solve the subproblem from times tk minus capital H maximum to time step tk. And this capital H maximum is a tunable parameter of this approach. This is the so-called history depth, because it controls how many time steps we will go back. And since this boundary condition operates just by solving another lattice Boltzmann subproblem, it is directly living and operating on the mesoscopic framework and not really derived from macroscopic hyperbolic system like the Lodi boundary condition. And I think this is best explained when giving a quick example of the working principle of this boundary condition. So here we will give an example for the nice D1Q2 lattice, and we will still consider the right-hand side subproblem. So the blue nodes are boundary nodes, and the black nodes are the bulk nodes, here given at several time levels, where the earliest time level is tk minus h max. And we are currently, we fixed here the history depth to 5, and we are currently at time level tk. And this in the DQQ2, we can hop to the left and right neighbors. So the population represented by this red arrow is missing. And in the context of this discrete artificial boundary condition, we will then proceed to create this lattice Boltzmann subproblem by going back this H maximum time steps and creating this lattice Boltzmann subproblem by essentially gluing the boundary of the original grid together with H max additional nodes, so that we end up with a grid that has H plus 1 nodes, and this will be the grid of the subproblem. And this will then be matched in time to eventually give this unknown population. However, before matching this in time, we need to initialize this in a meaningful way. And this is a crucial part of this boundary condition, actually, because what we are doing at the boundary node, this is actually previously computed information, because this is a part of the original lattice. So we have all the information about populations on this node at previous time levels. So this we can initialize with this information. And as far as the auxiliary layers are concerned, here we, for simplicity, can pose an external equilibrium. However, let me remark at this point that generally any external information that one might have about how the flow behaves outside of the computational domain can be imposed here for best results. And then we proceed to just march this problem through time. And as a boundary condition, inward pointing here into the subproblem from the left-hand boundary, we use the previously computed information from the original lattice at further down the lane time steps here. And eventually, we arrive at time level tk, and the population that is represented by this red arrow is now computed thanks to the subproblem. And as one can see, this is actually given in terms of the initial populations here. So the better we can do, put these initial populations here, the better the quality of this boundary condition will eventually be. And as I already mentioned, we for simplicity put an external equilibrium that is constant. One can, however, also use the populations from previous subproblems and do a kind of refresh and initialize these nodes here at this time level with known populations from previous subproblems. Yes, and this actually is very, very easy to extend to multi-speed stencils. Again, basically what one needs to do is scale the grid size of the subproblem by the maximum displacement of the stencil. Here again, the DQQ17 velocity stencil has a maximum displacement of 3 because you can hop up to 3 cells to the next neighbor. So naturally we have 3 layers of boundary nodes, and to ensure a history depth of 1, we need now 3 additional nodes instead of 1 additional node, because doing so we can ensure that in one step of the subproblem, no information that needs actual boundary treatment on the right-hand side of the subproblem will propagate to the computational domain of the original grid, namely the nodes we are actually interested in. So this was everything I wanted to say about non-reflecting boundary conditions and their basic ideas. Now I wanted to quickly turn to a numerical result I have, and this is the simulation of an isolated vortex that is propagated toward the right-hand side of the boundary. So we have a uniform density and we have a uniform background flow, and in the center of the computational domain we apply a velocity perturbation that is then advected towards the right-hand side boundary. Top and bottom boundary conditions are periodic, and at the left-hand side, we apply reference populations from a larger periodic simulation, so that the only real troublesome boundary, so to speak, will be the boundary condition we test at the right-hand side, namely the boundary conditions I just presented a couple of slides before. And we will then proceed to measure the relative errors in the density and streamwise velocity with respect to a larger fully periodic finite difference simulation to judge the accuracy of the boundary conditions. And yes, the first thing I want to present here is actually another open problem, because for the discrete artificial boundary condition, I'm showing you here the relative errors in the streamwise velocity in the first row and the relative errors in the density in the second row, and focusing now only on the right column where we are at a Mach number of 0.2. It looks actually quite good and promising, because for reference I included the extrapolation boundary condition as the green line as a reference to compare to. And on the right hand side here we can see that if we increase the maximum history depth from 10, which is presented by the blue lines, to 30, the red lines, and even 90, the black lines, then we see that the maximum error will steadily decrease. And after the vortex boundary interaction has passed, after some time steps, then the errors will quickly decline, and we also outperform not only in velocity but also in density by a good order of magnitude the naive extrapolation approach. So this is quite nice. However, if we consider the left column and look at the Mach number of 0.05, then we see that we are actually quite good to go at the maximum history depth of 10. And the strange thing now is that if we increase the maximum history depth to 30 and say 90, then we get even worse results, and even after the vortex has interacted with the boundary. So at later time steps, these errors will not decline anymore. So this is a behavior that I still need to understand what happens at larger values for history of the history depth at larger history depth at low Mach numbers. Let me also note that this behavior is not happening in the single speed case. So it looks like this is the problem due to the interaction of the several boundary nodes. Turning to a more encouraging result, actually, this is a very similar plot. So still This is the evolution of the relative L2 errors in density and velocity at the lower Mach number, considered 0.05. But now we are just cherry picking this discrete artificial boundary condition with the maximum history depth of 10 from before, still comparing against the extrapolation method for reference. But now we are also considering the Lodi method and the PML with the width of the damping zone of 10 and the maximum damping coefficient of 0.01. And the good news here is that all of the boundary conditions of the non-reflecting boundary conditions show a very similar trend. So they do a comparable job, a comparably good job of capturing non-reflective features, and they also share the niveau of the level of the relative error is also very comparable, with a slight edge for the perfectly matched layer. Let me also remark here that these parameters for the perfectly matched layer are only resulting from a very coarse scan and can probably be also optimized. But yes, from this picture, I believe you can see that there is a considerable gain when compared to extrapolation boundary conditions when turning to non-reflective boundary conditions. And this actually brings me to the summary of this talk. So what I have done here is extended several non-reflecting boundary conditions to the multi-speed setting. And for the perfectly matched layer approach, this is actually very straightforward because this is simple and has only a moderate computational cost, and it only manifests, the PML approach only manifests essentially in the modification of the collision operator. So it doesn't really know about multi-speed. However, the optimal choice of these damping parameters, namely damping strength sigma and damping zone width omega, W, needs careful analysis and will also depend on the stencil. So it's not clear how to choose them in the best possible way. The Lodi boundary condition has the nice feature of not relying on a grid extension. It's just relying on a characteristic analysis. That, however, needs to be done in several layers for the multi-speed approach. And I have mentioned before here, we also have some freedom on how to treat these several layers in a meaningful way with this. And I believe also at this point, more research needs to be done. And the Lodi boundary condition can readily be improved by reincorporating transverse velocities and viscosity after this characteristic analysis is done. So when I solve for this wave amplitudes, I can maybe improve on the accuracy of the scheme by re-adding this lost information I have discarded before. And finally, turning to the discrete artificial boundary condition, this actually is conceptually very nice because we are never leaving the mesoscopic framework. However, the subproblems are computationally very expensive, and especially for multi-speed stencils, the subproblems grid size will grow even faster. And another open problem we need to investigate is the behavior of this boundary condition at lower Mach numbers. And with this, I would like to conclude. And finally, thank you for your attention. And should you have any questions, I will try to answer them as best as I can. Thanks.
Thank you. Thank you very much, Dr. Klaas, for this nice presentation. So if you have, I think we have time for a quick question since we are a bit over time. So let's wait for about 1 minute.
Okay. Maybe share again the presentation.
there is a question you see in the chat.
Okay. If you published work on this, no. There is not. I'm guessing, do you mean a comprehensive comparison of all these boundary conditions presented, or a particular kind of boundary condition? Because for this, I believe I can go to the the references I've hidden from you so far. Sorry for that. So there is currently no work for me published on this. But if you are interested in a particular type of boundary condition, I can point you to this Najafi-Yatzdi paper for the perfectly matched layer approach, and a paper or a dissertation even from Daniel Heubes dealing with the discrete artificial boundary condition. And I've also seen, I hope this answers the question at least partially about this particular. Okay, so what is this? Sorry. Multi-speed Lodi. Okay, no. So far, I'm not aware of any publication for multi-speed Lodi, and I haven't published anything on this yet. So it's a new thing, really.
I think there is might be another question from Hosseini.
Yes.
Yes, there was a raised hand. Yes. Okay.
Yes. So thank you for your presentation. I just had a question. So if I refer back to the original paper by Poisson and Lele for Lodi or characteristic space boundary condition, they essentially consider the eigenmodes and the propagation speeds of the eigenmodes in the system to let them out of the boundary. And in their system, it's a compressible flow. So the eigenmodes that they have basically are acoustic, convective, et cetera, and energy. In your case, you have a Q17. You have more eigenmodes, right? Proper eigenmodes with their own velocities. Do you think that solely considering the physical macroscopic moments, such as pressure, et cetera, is enough to let all of the modes go out of your boundary, or should you consider the full eigenmode system?
Okay, this is actually a good question. I'm not sure. So far I've taken the rather simple approach and just gone with essentially posing the very same structure they did. I'm not sure if it's enough. I can't fully answer this, but I have to look into this, I think. But it's a good remark. Thanks.
Thank you.
Another question in the chat.
You have a fixed sigma in the PML region. Yes, okay, so this, I think I did not mention this for reasons of simplicity. So this sigma will be dependent on the distance to the boundary, in the sense that I'm using a quadratic ramp up of the sigma to this maximum value, so that there is this, like a smooth transition from the bulk towards the damping domain. So the further you are in this damping zone, the further this, then you quadratically ramp up to this maximum value of the sigma.
Okay. So I don't see other questions. So I think we can all thank you again for the nice replies. And okay, so this is the last talk of today's session. And then we see you all tomorrow morning for the plenary talk starting at 9:20. So thank you all very much for the participation. Bye-bye. Have a good evening.
Goodbye. Have a nice evening, and see you tomorrow, I hope.
See you.